Okay, I'll write while talking. So what I was saying, we have seen in LP and QP necessary. This is part 4 of your course. Necessary and sufficient conditions for LP you've seen. Today you'll see for QP as well. Then we did simplex for LP. And today we are talking about duality and interior point method again for LP. So in this, duality principle will be clear to you. Like I said, Lagrange multipliers, KKT conditions, if these keywords are synonymous to optimization course, duality is also synonymous. So the idea behind this is sometimes the indirect solution is more efficient. There are two different perspectives. So there is a primal problem which we solve, which you already see with me, and you get Lagrange multiplier from the necessary and sufficient condition. You use them as params to your another problem, and then you get your dual problem. So that is how we are doing. So we, rather than solving the original problem for x, lambda and mu, which we do, we are going to transform it in terms of the Lagrangian and the Lagrange multiplier, and that's called the dual problem. Sometimes solving the dual problem is easier, which you'll see in a minute. So we'll first write a theorem. This is duality in convex programming. This theorem is for CP. Although we are in the linear programming section until this point, but we are generalizing this to a convex program because a linear program is always a convex program. So the theorem says that x star be the minimizer and lambda star mu star be the associated Lagrange multiplier of this problem if x star is a regular point of constraints, then x star, lambda star, mu star solve the dual problem, which is given by maximizing the Lagrangian with respect to x lambda mu subject to gradient of the Lagrangian with respect to x equal to 0 and mu greater than equal to 0. So this is your dual problem, and we also know that the minima is nothing but the Lagrangian of x star, lambda star, mu star. That's the theorem. So this is in addition. So how does the problem look like? If you look at the optimization problem, what's the difference from a standard optimization problem and this? Yeah, we'll come to the dual. If you look at only this problem, this is not the most general convex program. Why? What is a convex program? Fx should be convex, the linear constraint should be convex, and the equality constraint should be convex, and the inequality should be concave. That is how we defined the convex program, if you remember. This Navinar would have defined with you, the objective function convex, the equality constraint convex, and the inequality concave. But if you look at this, it's saying this is the objective function which is given to be convex. These are the inequality constraints which are concave, correct? But for the equality constraints, it's not saying it's general, it is writing them as linear. This A and this A are different, no? This is equivalent to writing Ax is equal to B. That's the constraints. So the equality constraints are not in general convex, they are linear. So the theorem doesn't hold if you just write any equality constraints. Sorry, it should be 0. You're not telling me anything. Otherwise, it's not a constraint, right? Correct? Everybody clear that it's not true for general equality constraint, it's true only for a linear equality constraint, not a general convex equality constraint. Okay, so that's one thing. Second thing which Shaurya just pointed out, it's saying that instead of minimizing the function, we are going to maximize its Lagrangian. So you can see the duality coming into play. Duality means another side. English word would be, like the dual of India is US. You can think of it that way. It's on the other side of the globe. So, or India is the dual of US, or North America is the dual of South America. Whichever perspective you want to see, one is north, one is south. So here you're minimizing f of x, here you're maximizing. Here you're working with the function, here you're working with the Lagrangian, and the constraints ai and cj are not playing around with the gradient of the Lagrangian, and the Lagrange multiplier mu is playing a role. Once we apply this theorem to our linear program, then you will be able to appreciate more why we are doing this. What gain I am getting out of it. Right now you can only see it's a dual problem. It's a different perspective. This you can see. This you can see that the prior problem gives you a Lagrange multiplier, you use them as a parameters, you get a dual problem. But whether it is more efficient or not, this will be more clear when I apply this to our standard linear program, which we'll do after proving this. Is that okay? So, yeah.
Equality constraint, because it is linear, it would automatically be convex.
That's why it's a convex program. It's convex and concave both. So we're using this as convex, this is convex, this is convex, this is convex, so this is a CP. But what I'm saying that it's not true if I just write this. If I write this and I say AIs are convex, then this theorem will not hold. The equality constraints have to be linear for this theorem to hold. Is everybody okay? Who knows, maybe in future somebody proves this, that it's true for general with adding a couple of more constraints. That is how research goes. This is AI transpose x minus bi equal to 0. This is nothing but AXCP. Everybody okay? active, all. When we say regular, then it means it's true, it's regular for all the equality constraints and those which are active at extra. That is always true. Can you try to prove this? So let's try to first, and finally it's saying in addition, you have to find the minimizer. The fx star is the Lagrangian of this. So let's write the Lagrangian, substitute the x star, lambda star and mu star. Can you show me how to prove this part? Then we'll come to this, how to transform this guy into this guy. Okay, help me then. If I have to write Lagrangian of the function, what is it? Tell me. It is fx minus summation of I going from 1 to r lambda I times ai of x minus summation j going from 1 through s mu j of cj of x. Everybody with me? This is what we wrote in the very first lectures which I did here. Now, if I substitute this as x star, lambda star, mu star, then what happens? Sorry? It has become fx star. Why? Correct. So you recall the necessary conditions now? That this should be true. This should be equal to 0. What are the 5 necessary conditions for a minimizer? Remember, x star, lambda star, mu star are the minimizers, which means they will satisfy the necessary and sufficient conditions. What were the 5 necessary conditions? The equality constraint should be true, the inequality. This is the Lagrange multiplier condition, although we have not put the gradients on them. And then there was the complementarity condition and the non-negativity condition. So like Curves just said, aix star would be 0. So you'll have f of x star minus 0, and then what will be this? Again 0 from the complementarity condition. So this will be 0. So the first thing is easy to prove, है ना, that fx star is Lagrangian of this. Everybody okay? Now we're going to come to this guy, the bigger thing. How this transforms to this. है ना? Okay. Let's write this thing. Lx star, lambda star, mu star. Okay. So this is equal to fx star minus summation I is equal to 1 through r lambda I ai of x star. Is this okay or not okay? Sorry, we're not going to gradients. Sorry?
Which part?
This equation. Yeah, correct. That's what I'm saying. This is anyway 0. So this part is okay, right? What did I change here as compared to here? I removed the star from the lambda. I'm putting not the minimizer lambda Lagrange multiplier, but any Lagrange multiplier of the corresponding to the equality. You'll see in a minute why I'm doing it. Huh? Now what I'll do, can I write this as greater than equal to fx star minus summation of I is equal to 1 through r lambda I ai x star, because this term is 0, minus summation j is equal to 1 through s mu j cj x star. Can I write this by adding this term? Why? Because mu j is greater than 0 from the condition which we are trying to enforce, and so if mu j is greater than equal to 0, then I can write this, because cj x star is anyways greater than equal to 0. Remember, mu j x star is greater than equal to 0, not any mu j. The necessary conditions said that x star, lambda star, mu star give you a minima or are the minimizer if those 5 condition or 6 condition hold. So it doesn't hold for any mu. So if I force the mu j to be greater than 0, I know Cj star has to be greater than 0. It's a minimizer. It has to be a feasible point. It should satisfy the inequality constraint. So this whole thing will become positive. When I subtract something positive from this, then I get a greater than equal to sign. Everybody with me? Yes or no? So what can I write? So if this is true, then I can write that L of x star lambda star mu star is greater than equal to, what is this guy now on the right hand side? Right. L of x star lambda and mu without the stars. Everybody with me? Call this as equation 1. ठीक है? Alright. My goal is to eventually get a relationship between the Lagrangian x star, lambda star and mu star, because I know Lagrangian of x star, lambda star, mu star is fx star, and I am trying to minimize f of x, or I am trying to find this f of x star. So I have to somehow bring it in terms of the Lagrangian of x, lambda and mu. So once I had it in terms of x star, lambda star, mu star, I was able to convert the lambda star and mu star to lambda and mu. Now I try to get rid of this and get a relationship between this and Lagrangian of x, lambda, mu, so that I can go to this form. This is where I am going in the proof. Can everybody see? Okay. So now we'll do one more step so that we can get a relation between this and Lagrangian of x, lambda, mu. Okay. So far so good. So what I'll do is I'll write L of x plus x star minus x comma lambda comma mu. What is this? This is nothing but this guy. Sorry, this guy. Now I'm working with this guy. X star lambda comma mu. The x's will cancel out. Huh? So I'm trying to get this in terms of Lagrangian of x lambda mu without a star. Okay. So if I have to apply Taylor on this, what will I get? X lambda mu plus what else? We'll get gradient of, we'll get, this is your delta, है ना? We'll applying Taylor only along the x direction. So if it should be delta times gradient of this, है ना? So I'm going to write this more explicitly. So I'll write this as x star minus x gradient of the Lagrangian with respect to x, because we're doing with respect to x, x lambda and mu. X lambda and mu. This is x plus delta. Then if I carry the second term, what is the second term? Half of x star minus x transpose Hessian of the Lagrangian x lambda mu times x star minus x, correct? Plus order of norm of x star minus x cube. Huh? Okay, now from the theorems which Devinath would have proved with you, for the sake of ease, let me just write, okay, let it be. This is delta. So out of this and this term, which term will dominate? This term will dominate, right? And what do we know about this term? Let's write the L of x. L of x is f of x minus summation mu I is equal to 1 to R AI transpose X minus BI minus summation J is equal to 1 through R mu J Cj. Correct? This is your Lagrangian, which was already written actually. I didn't have to write. Except that I have written this the linear function which is given in the constraint rather than a general AI. So now this is convex, correct? And this is convex, or I can say concave also because it's linear. So with the negative sign, what does it become? The scalars don't matter, hai na? They will become convex. What was Cj? Concave. With the negative sign, it became convex. So the Lagrangian function is also convex because it's a linear combination of convex functions, correct? Now what do we know about a convex function? The Hessian is positive definite. What is the definition of positive definite? You multiply a non-zero vector on the left and right, the whole thing is greater than 0 strictly. Or positive semi-definite. If it's convex, then the Hessian is positive semi-definite, which implies that if you multiply with a vector on the left and the right, the whole thing is greater than equal to 0. So this whole thing is greater than equal to 0, and I don't care about this because this term will dominate anyways. Yes or no? Here we are working with the Hessian with respect to x. So, you could be with respect to lambda, with respect to all the Hessians will be positive semi-definite. Everybody with me? So now if I have to write this term, what is this? This is greater than equal to L of x comma lambda comma mu if gradient of the Lagrangian with respect to x mu is equal to 0. So if I force this guy to be equal to 0 and this thing is anyways greater than 0, the two together are greater than equal to 0, then this will become greater than this term because you're subtracting something positive. Correct? This is 0 because we are assuming this, and this thing together, the two terms together are positive, so and there's a negative, so you subtracting something positive from this, so it will become lesser, so this will be greater than this. Yes or no? Everybody with me? Aditya lost. This is what the Taylor says. No. Sorry, it shouldn't be minus.
It will be plus only, but still that whatever expression you said was actually true for plus.
It will true for plus, not for minus. Because we are removing something. Sorry. It's all plus. This thing is greater than 0. If you remove something, then it will become lesser. So this will be greater than this. Ask me, I saw lost face. I wrote it wrong by mistake. For example, this is 100 is equal to 10 plus 5. And you're dropping 5. So you're saying this is greater than 10. This is what we're doing. Correct? Everybody can see? There was no minus, sorry. So now what do we get? Why did I force this? Why did I make this equal to 0 and I made this equal to 0, greater than equal to 0? You look at the constraints of the dual problem which I have just removed. It says that gradient of Lagrangian with respect to x is 0 and mu j is greater than equal to 0. So I'm already adding those constraints as I'm trying to prove this. Okay? So this is second equation. Now if you look at the first and the second, what do you get? The first equation says the Lagrangian with respect to x star lambda star mu star is greater than x star lambda mu, and this is the same thing. Lagrangian of x star lambda mu is greater than Lagrangian of x lambda mu. So the 1 and 2 together are giving you that the Lagrangian of x star lambda star mu star is greater than equal to Lagrangian of x lambda mu. Correct? Now we are done. Okay. So if I have to write, what do we know? We know that L of x lambda comma mu is less than equal to the max of L of x lambda comma mu. Correct? And we also know that L of x comma lambda comma, this is by definition the maximum of the function. And from 3 we know this is less than equal to L of x star comma lambda star comma mu star. This is using 3. Correct? So what do we get? X. So if we make maximum of x lambda comma mu L of x comma lambda is equal to mu is equal to L of x star lambda star mu star, then above true. So we already know that L is less than its maximum value, and we also proved that L is x lambda mu is bounded by L x star lambda star mu star. So if I make this guy equal to this guy, then we are satisfying this equation, right? Yes or no? Everybody? What is this guy? Fx star. What is Fx star? Minimum of f of x. So you've converted the minimization problem to a maximization problem. Only if subject to, what were the things which we assumed in proving this? We assumed this and we assumed this. So we have to write those constraints. So subject to gradient of the Lagrangian with respect to x is equal to 0 and mu j is greater than equal to j is equal to 1 through s. So we transformed the minimization problem to a maximization problem of function. We are no longer playing with the function, we are playing with the Lagrange multipliers. Now what we're going to do, we're going to take this theorem and apply it to our linear program and see the benefit of it. Okay? Any doubts? Then ask me, please. So then the things would be much better defined for you. So we're saying, doing an example, we did the introduction. So we're saying find dual of standard LP. So your standard LP is minimizing C transpose X subject to Ax equal to b, x greater than equal to 0, C is belonging to Rn, A is belonging to R cross N, and then R is less than N is given to you. Can you try to find the dual? I'll come in a minute. Or let me write it down, then you tell me whether this is true or not. So the solution is, so okay, I'll help you get started at least. Lock. Okay. So what do we have to do first? We have to find what? To find the Lagrangian of it, right? This is the dual problem. So the L of x lambda comma mu is what? Tell me. C transpose x minus, sorry, lambda transpose Ax minus b, correct? So lambda 1 times the first row plus lambda 2 times the second row plus lambda r times the last row. When you put it in a vector form, it's lambda 1 through lambda far, and these are all the rows. Summation. And minus what? Mu what? Mu transpose x. The CJs are just x's here. Mu1 x1, mu2 x2 till mu n xn. And I've written it in a vector format again, mu1 to mu1, x1 to xn. Can everybody see this? Okay. We'll try to simplify this further. So what I'll do is write this as x comma lambda is equal to C transpose x minus x transpose A transpose minus B transpose lambda minus x transpose mu. Does it change anything? These are inner product between two vectors, lambda transpose Ax minus B, so I can write Ax minus B transpose times lambda. So I've just switched A transpose B is B transpose A. When you pull the transpose inside this, it will be X transpose A transpose minus B transpose times lambda. Yes? Similarly, instead of mu transpose X, I can write it as X transpose mu. Like Shaurya said, it's a scalar. Correct? Yes or no? So we'll try to pull some elements out. We'll also write this as X transpose C. So now what can I pull? X transpose. So this will be C minus A transpose lambda minus mu plus B transpose lambda. Correct? Now this is the maximizing function. Let's try to write what is the gradient of this. What is the gradient? It is just this vector. Again, this is A transpose B, and if you take gradient with respect to A, then it will just turn out to be B. This we have done it many times, right? So this is nothing but C minus A transpose lambda minus mu is equal to 0, and the constraints you had was mu j's are greater than equal to 0. Or if you want to just write mu's, that also is fine. So what I'll do, I'll take this guy and substitute it in this. Correct? Because I have to anyway satisfy this constraint. So your optimization problem is maximize B transpose lambda subject to C minus A transpose lambda minus mu is equal to 0 and mu is greater than equal to 0. So this is your dual problem. So one thing to notice between the primal problem and the dual problem is, what is the most starking difference between the two? Well, min max is there. Huh? Correct. There is no x playing a role here in the whole thing. X was n dimensional. What is the dimension of lambda? R. So imagine x being a million and the number of constraints are only 100. So minimizing a function which has a million unknowns, you're minimizing a function with only 100 unknowns. Although this will still be million because this is n, 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 and n. So the constraints will definitely carry those dimension with you, but the objective function dimension is dramatically reduced. So that is one of the advantage of dual problems. Sometimes they are more efficient to solve. Is that okay? All right. You do so this was the example. You solve it and tell me with another example. Then I'll tell you what are interior point method. Then we'll stop. We'll not run too much. So we write minimum of x1 subject to x1 plus x2 is equal to 1, x1 comma x2 is equal to 0. So find the primal dual solution. This is actually motivating to you towards the interior point method. You apply the necessary and sufficient conditions for a linear program on this and tell me what's the solution. Did anybody solve it? What do you get? Let's apply the KKT condition. Okay, I'll not write this. What were the KKT conditions? We'll write that x1, the equality constraints are true. Then we also want the inequality constraints to be true. Then there was gradient of the function is linear combination of gradient of constraints. So gradient of the function is 1, 0. With respect to x1 it's 1, with respect to x2 is 0, is minus lambda times with respect to x1 it's 1, with respect to x1 it's 2 is 1, minus mu1 with respect to x1 1, x2 0, minus mu2 0 1 equal to 0 equal to 0. Then you had x1 mu1 is equal to 0, x2 mu2 equal to 0, and you had mu1 and mu2 all this greater than 0. Correct? Those were the KKT condition. I've just written them in a slightly different order. This is the equality constraint. These two are inequality constraints. I've written them separately. This is the Lagrange multiplier condition. Gradient of the function is linear combination of gradient of constraints. The complementarity two conditions, and the non-negativity condition, I have written them separately. Now why? So this you can solve, hai na? Once you solve for this, you will get the value as, that's not too important. So once you solve for this, you will get as x star is 0, 1, lambda star is 0, and mu star is 1, 0. You will get another solution where one of the mu's will be negative. Did anybody solve it? Yes or no? So anyways, this is referred to, they're calling this as a primal dual solution because lambdas and mu's are also there. Nothing fancy about it. There will be another solution where mu1 will be minus 1. So that solution will not be valid. So we are only looking at this. So why did I write this problem? You could have actually, plugged this inside this and solved this also, that you could have done algorithmically or what. We're trying to motivate you towards something called as an interior point method. This is the last thing, so I'll take 5 minutes and finish.
So,
Yeah.
so in this question, what have we done differently from how we used to solve it?
Nothing. This is something which you had done in the very first lecture of the necessary and sufficient condition. Nothing. The only thing I have done is I have written the equality and the inequality constraints separately. Otherwise, you will write the equality, two inequality here, the Lagrange multiplier, the complementarity, and then you'll write the non-negativity constraints here and solve the 5. These are necessary and sufficient.
Simply solving the KKT.
Simply solving the 5 necessary and sufficient, the KKT conditions. The only thing what I have done is I have written them separately. I have written the equality equations and the inequality separately. This is what.
We didn't use that.
No, we have not used anything of this. We have not used it. That's what I said. Primal dual is because there is a dual variables. These are called the dual variables, the Lagrange multipliers. It's just a nomenclature, nothing new. We are solving the primal problem and the dual problem together. So that's why it's called primal dual. Most of the ones where you apply necessary and sufficient will be called primal dual. Now you know what dual is. Dual is where the Lagrange multipliers play a role inside the objective function as well. That is what a dual problem is. Remember, maximum of Lagrangian subject to gradient of Lagrange. That's the only thing. Now let's try to write the interior point method. To write the interior point methods, we'll recall the KKT. So if I have to write the KKT for the linear program, the 5 conditions, it will be ax minus b is equal to 0, x greater than equal to 0, and it was C minus A transpose lambda minus mu equal to 0, and it was mu j xj equal to 0 and mu j is greater than equal to 0. Why the interior point methods come after dualities will also be clear in a minute. Let me hear. Everybody okay? Equality, inequality, Lagrange multiplier, complementarity and non-negativity. What, like I did in this solution, I separated the equality and the inequality. Correct? So I'm going to separate them. This is equality, this is equality, this is equality, and these are inequalities. So I'm going to write them separately. Is that okay? So instead of writing C minus A transpose lambda minus mu, the convention which is followed is take it to the other side and write A transpose lambda plus mu minus C equal to 0. It doesn't matter, but the convention in the book is that, so I'm sticking to this. So what I'll do, I'll take these and write them as a function. So I'll write this as a function of x lambda comma mu, and I'll write it, if I'll first write this equation, A transpose lambda plus mu minus C. Then I want to write the second equation, Ax minus B, and then I have to write these guys. So if I have to write these set of variables in a matrix form, how can I write it? I have to write something here in place of this. I first wrote this guy, then I wrote this guy, now I'm writing this. You can write it in any order. You'll see in a minute why this has been written this way. And then I took the inequality constraints and I wrote them separately. Okay? So how can I write mu1 x1, mu2 x2 all the way till mu n xn in a matrix format? In the diagonal elements. So what I could do is, I've got mu1 x1 till mu n xn. I can write this as mu1 through mu n x1 through xn, but this will still be a matrix. It will be a matrix of mu1 x1 on the diagonal element. How do I make it a vector like this? Sorry? 1 1 1 column vector. So if you multiply this with 1 1 1 1, these two are equivalent. Correct? This will just be mu1 x1, mu n xn on the diagonal. Now you multiply with a vector of 1s, it will be mu1 x1, mu2 x2, mu n xn equal to 0. Correct? This I am going to call this as capital lambda, and this I call it as an x. This I call it as an E vector, which you have already seen. Yeah. You can write it mu transpose x, but I want to write it in the matrix format. This is still an inner product of two vectors. So I want some matrices here, because I want to take a Jacobian of that. Huh?
Transpose x want to be all of this individual.
Oh, sorry. Yeah, sorry. Correct. Wrong. These are individually equal to 0. If I write mu transpose x equal to 0, then it's saying mu1 x1 till mu n xn equal to 0. This is not what we want to do. So you can't write it. Correct. Thank you. Okay? So what is this? This is nothing but x lambda times E is equal to 0. I've just swapped the order. Hai na? E is the vector of ones. So now what do the interior point methods do? What is this? This is a system of Non-linear equations. How do you solve a system of non-linear equation? What's the best way to solve it? System of non-linear equations equal to 0. Sorry?
So how?
Non-linear because there is a product of x and mu. So it's we call it as mildly non-linear because this is linear, lambda is linear, it's linear, x is linear, but there is a, in fact, there is a term of bilinear also. I'm not going to go into that. It's not highly non-linear. There is no cubic or logarithm or sine functions combination. There is a combination of two variables together. So it's mildly non-linear, but it's still non-linear. So if you recall your numerical methods from your second year or first year, whenever you learn, if we have to solve for fx is equal to 0 by Newton's method, then what's the iterate? Can anybody recall? How do you solve the Newton's method? So okay, before I go forward, what the interior point methods does is it solves this equation and then it assumes, let me first tell you how it proceeds, then we'll go about solving. It solves this equal to 0 by forcing x and lambda strictly greater than 0. So it solves for f of x comma lambda comma mu equal to 0 by strictly forcing this is greater than 0. So what it is doing is it is somewhere inside this feasible region, but it is strictly inside it. Why is it strictly inside? Because then the constraints would have to be valid, active on the boundary. What are your constraints? X are the constraints, right? If you look at the original problem, X are the constraints. If you look at the dual problem, what are the constraints? The mu's are the inactive constraints. Remember, maximize B transpose lambda subject to gradient of Lagrangian equal to 0, mu greater than equal to 0. And if you look at the primal problem, it is minimize C transpose X subject to Ax equal to 0 and X greater than equal to 0. So if I am forcing X greater than equal to 0, then from the primal problem I am not on the boundary. If I am forcing mu greater than 0, then I am not on the boundary in the dual problem as well. Correct? Which means that I would be somewhere inside the feasible region if I force this. Yes or no? Everybody understanding why it's interior? X greater than 0, mu greater than 0. Primal problem constraint, dual problem constraint. So what this is doing is the interior point method finds the solution of this by forcing this, but we know that the solution of the LP lies on the boundary. The solution will not be in the boundary. Those would have seen the PDFs which I had uploaded when I talked about F simplex. So what it does is it keeps iterating inside, and upon convergence it will go to one of the vertices and give you the solution. So this is dramatically different from what we do in the simplex method, where we find one vertex and do all that effort in finding one basic feasible point, then go from one basic to the next to the next. This guy doesn't think too much. It says I want to separate the necessary and sufficient conditions based on equality and inequality. The equality ones, because they are mildly non-linear, I am going to apply some non-linear solver to it, but along the way force this to be strictly greater than 0 and keep moving. It can also force this equal to 0 so that it's boundary. But then the search space takes too much time to converge. So what it does is it says I'll let it be free, go as fast as you can to the vertex and then converge. Is it making sense? So that's the I just wanted to give you a flavor of what is interior point method. I'm not deriving the algorithm, I'm not making you code. I'm just telling you that it's an alternative to the simplex methods, kind of methods which work on the boundary. This guy works inside the region. Does that make sense? So now how to solve this? So you will solve this by the Newton's method. So if I had to solve some function g of x equal to 0, what did the Newton's method direction says? I'll say g of x1 is equal to g of x naught plus Taylor of x1 minus x naught g prime of x naught, right? This is the Taylor if I apply on it. Yes or no? This is nearly equal to, I am at some x naught and I am going towards x1, so this is the difference. There will be higher order terms which I have not written. G is a function of one variable and it's a scalar function as well. So then how did we derive the Newton step? We forced this equal to 0. Then we said x1 is equal to x naught minus fx gx naught divided by g prime of x naught. This was the Newton iterate if you recall your numerical methods. So if I have to apply the numerical Newton method on R fx, then what did it be? Tell me. So we'll say x1 lambda 1 mu 1 is equal to x naught lambda naught mu naught plus this delta x delta lambda delta mu. This is your delta, correct? So what is your delta x delta lambda comma delta mu? Should I write this? Should I write this? Correct? How is it correct? There G was going from one-dimensional space to a one-dimensional space. Here your F is going from how much space? X lambda mu 2n plus r space to r n n 2n plus r. Correct? So is there a derivative of a function of many variable and a vector valued function? What is the equivalent of a derivative there? Jacobian, right? So I am not writing this correctly. I will write this as equal to minus Jacobian of f at x naught comma lambda naught comma mu naught inverse times this. Correct? Everybody with me? Now what is the Jacobian of this function? You tell me. What's the Jacobian? Tell me. What is Jacobian? You take every row and differentiate with respect to all the components, write them row wise. So if I am going to do the Jacobian, let's do with respect to, let's not write because I have written lambda mu. If I want to write the x first, then I should write this as ax minus b and this should be a transpose lambda plus mu minus c. So if I do with respect to x, what will I get? A0 0. Then I do with this is, well, it doesn't matter. then I do this guy with respect to x, I'll get 0. This guy with respect to lambda, I'll get A transpose. This guy with respect to mu, I'll get identity. Then I'll take this guy with respect to x, I'll get this gamma, capital gamma. This guy with respect to mu 0. This guy with respect to gamma, it will be x. So this is the Jacobian. So now it will be more clear why I had to write it in the matrix format, because I had to get the Jacobian matrix. So I had to write those equations in a matrix format. Okay? Now let me just summarize the whole thing for you, because there were a lot of disjoint components. You can come and have your lunch and come late also, and I know I'm leaving you late. So you can come at 1:40 or so. Okay? So what did we first do? We first took the original problem, minimized. We first told you what is duality for a convex program. That's the very first thing we did. In that I said the duality theorem, where you minimize the function and write the constraints and find the maximum of the Lagrangian, doesn't work for a general convex program. It only works where the equality constraints are linear. Okay, that's the very first thing to note. So you, instead of writing minimize f of x, ax equal to 0, cj greater than equal to 0, fx and fx concave, cj, fx convex, cj concave, you got maximizing of the Lagrangian subject to gradient of the Lagrangian 0 and mu greater than equal to 0. That is the general duality theorem. Once we applied that duality theorem to the linear program, minimize c transpose x subject to ax equal to b and x greater than equal to 0, we got the dual maximizing of b transpose lambda subject to a transpose lambda plus q minus c equal to 0 and mu greater than equal to 0. Correct? So the gain there was that the objective function didn't, or the dual problem did not have x anywhere to play a role. So in that sense, the objective function became of a smaller dimension, because instead of working with an n-dimensional objective function, you were working with an r-dimensional objective function. Although the constraint did carry all the n dimension which we were talking about. That was the second thing we do. The third thing we are talking about is the interior point method. Now the interior point methods, they start again, we go back to the necessary and sufficient condition. Like we did with the simplex method, we started with the 5 necessary and sufficient conditions. We were able to satisfy 4, and the 5th one we iterated. The biggest challenge in the simplex problem is find that one starting basic feasible point, find that one vertex. Instead, the interior point method said, I'm going to take all the 5 conditions, separate the equality and the inequality, solve the equality once by some nonlinear solver. I'm writing it as a Newton's method. You can use any other method. You can use steepest descent, gradient descent, or higher order methods as well. It doesn't have to be Newton's always. And then, instead of forcing the inequality constraints, the x and the mu's, which are playing a role here, instead of making them equal to 0 or greater than equal to 0, I'm going to force them so that they stay inside. I have not given you the motivation of why I am forcing this. It has better properties to solve. What it does is that if I force this equal to 0, I'll stay at the boundary and take a lot of time. By forcing this strictly greater than 0, I'll say maybe the solution is here. You jump to the closer to the solution and find the 2 steps rather than taking 100 steps. Why this theory is coming after duality is because both the primal variable and the dual variables are playing a role here. Is that okay? Although they were playing a role in simplex as well, but somehow it is given after duality usually. Everybody okay? Yes? Too much? Okay, alright. So I'm seeing a little, I know that although you have more than a week to study, the exam is next Monday. So this is part of the syllabus, the duality is part of the syllabus, and so is the interior point method, and QP will also be, which we'll do. So those who are not there, I'm hoping they'll study from the recording. So you can come back at 1:40, or if this is less, 1:40, okay? Is that enough time for you to eat food? Or 1:45 is better? Huh? Yes, we'll take your opinion. 40 is fine. So we'll come back at 1:40, finish the quadratic program, and then we'll do the tutorial on the quadratic.
I had a doubt on the degeneracy part.
हाँ ask me.
So there exactly what is the condition for degeneracy?
Degeneracy is when any of the active constraints come into your B set.
Okay.
If